Okay, so we're going to do a little Matlab example about second order ordinary differential equations, and here's what we have before from the previous part, and we're going to break it up into these two different ways. Okay, and so we've got these two examples right here, or rather these two first order ordinary differential equations, and so we're going to spend some time just going off and trying to use some of these methods that we talked about to try to solve a second order ODE. All right, so I've got my new second order ODE example script right here. It's all empty, so I need to go off and get some stuff from the other example. Okay, so I've got CLC. This is second order ODE examples. All right, I clear my command window, I clear all my variables, I close all my figures, and now I need to spend some time actually getting some anonymous functions that are both first order, and they're both relatively easy. Okay, so beforehand, if you recall, there was this idea of the function name. I'm actually going to call it dy dx. Okay, and then I'm going to have that at symbol again right here. And I'm going to put a function of, it's going to be a function of x, y, and v. Okay, I'm just going to follow this little example right here before. And it returns a v. All right, and then I'm going to have a dv dx, okay, right here, and it's going to be a function of the same things. So I'll copy and paste that, but it's going to be a function of minus 0.6 times v minus 8 times y. All right, and so those are my two anonymous functions. Okay, instead of working with this nasty second order ordinary differential equation, I've got now two first order ordinary differential equations. All right, well, I don't know what the exact solution is right here. Okay, and well, I mean, I guess we can go off and try to find it out. Okay, but right now I'm just going to try to see what happens if I can use my methods to try to extract out what the approximation is. So in other words, I don't know the truth, but I'm going to try to use the tools to extract out what the truth is almost. All right, well, I'm going to come over here and I'm going to pull out my Euler method. All right, so let's grab it right there, and I'm going to keep my dt to 0.1. I need to define my time initial and time final, but in this particular case, I don't have time. Okay, so I need to actually set it with respect to x. Okay, so I'm going to have a little dx of 0. No, I'll make it big actually first. 0.5. Okay, and then x, okay, is going to be from x initial all the way to x final. All right, well, if I have those, I need to define what those are. So x initial is going to be at 0, and I'll go to x final. Right now, I'll just set it to be at 5. I'll suppress all these things right here. I'll even suppress dx. All right, and then y, okay, is what I'm really after, because that is the variable of interest that I have in my second order equation, which means v right here is going to be kind of a temporary one, but I'm going to plot that as well. All right, so I've got x, I've got y, I've got y initial. I need to define what my y initial is. Okay, in this particular case, I'll just set it to be 2 for the time being. Okay, we'll talk about here in a second as to why I might need to have something else. All right. And now, okay, I've got my y initial, I've defined my y, and now I need to go off and update my Euler's method right here. So I'll just do Euler's method to remind myself that I'm doing Euler's method before I go off and do something else. Okay, well, let's talk about it. Well, I've got two variables. The first one is going to be y I plus 1, okay, equals yi. Okay, everything is the same right here. That all works out well. But now this function right here has to be a little bit different. Okay, and in fact, I need to use my dy dx function. Okay, and it's a function of three things. Okay, so I'm just going to copy and paste it right here. And I'm going to take my i's and pop them right here. Vi, yi, and xi, and of course I have to multiply it by not my time, but of course my other dimension, taking on the denominator of dx. Okay, so I've got my function. It's defined up here. That's good. I've got x, which is defined right here. That's good. My y is going to be defined right here. And now I've got this v thing. Okay, so v, well, what is v? Okay, well, v is going to be one of the dimensions of interest. It's an intermediate variable, but I need to know what it is at vi and vi plus 1 and vi plus 2 and so on and so forth, which means then that I need to have a v vector as well. Okay, so I'll come and copy those over. I'll keep it set at 0 right here. It needs to have the same length of t, but again, t is not defined. I need to make this into an x. All right. Now, if v has this length of whatever x is, okay, I needed the exact same thing, okay, for v. So at the very beginning, I have some sort of vi, okay, and then I add a slope to it. Okay, in this case, it's going to be dv dx, okay, a function of all these other things right here, times dx. Okay, so essentially then I'm doing Euler's for each one of these, okay, at the exact same time, or close to the exact same time, but I can't do this one until I've done this one, and I can't do this one until I've done this one after as well. All right, well, let's take a look at what else we've got for our y. Well, I've got this y initial, which means this v, okay, I also need to have some sort of v initial. Okay. So v initial, I don't know, what could it be? Could it be 0? Could it be something? Well, we'll talk about that later on, but I'll assume then that right now it's given and it's 4. Okay, we'll change those here a little bit later on. Okay, so what am I left with now? Well, I've got my v initial, and now I need to update what my v1 is. So v1 is equal to nothing more than v initial. And be careful about the y's and the v's because they can sometimes look very similar. All right, well, assuming that I've done everything correctly, then I can go off and I can make my figure. Okay, I need to plot, and I'm going to plot everything with respect to x. So I'll plot xy, okay, and then I'm going to hold on, and I'm going to plot xv, okay, but I'm not going to plot that right away. I'm just going to suppress it. We're going to take a look at what happens first of all. All right, I'm going to hit run. Let's see how well I do. Oh, undefined functional variable dt. Let's go back and find my dt. It's going to be on line 15, and sure enough, this is that increment right there. I need to change that into dx. All right, bringing it over right here. Okay, we can see some interesting things. First of all, I haven't labeled things. We're going to do that here in a second. And it looks like there is some sort of interesting sort of curvature, okay, right here around 3 to 4 to 4.5 seconds. So I first of all maybe need to increase my resolution, okay, the coarseness of what I've got before. So let's go off and do those couple of things. We'll talk a little bit more about it here in a second. So I'm going to label my x to be nothing more than x, not time anymore, and label my y as y. Okay, and I'm going to change this to be 0.1. Okay, and now I've got something also really interesting, okay, is that now the form is even looking way different, okay, because I'm now going from 0 to 5, not in terms of time, but 0 to 5 in x. Okay, and it looks like I have some sort of oscillating result for my answer. That's kind of interesting. Let's go off and explore it. First of all, maybe we'll make it even a little bit tighter. We'll do 0.01. Okay, and now I'm looking at it again, and sure enough, it looks like it's still oscillating, but now it's doing something even more different than what I had before. It's almost like it's a decaying, oscillating function. Okay, well, let's go off and make it even more resolved here. Hey, it looks like now it's finally reaching some sort of steady state. And so if you recall from the previous values, Euler's method has some problems because if your time step is too large, well, it might not be stable, it might give you erroneous results, it might be a long ways away from the particular real-world example. Okay, well, let's kind of explore this a little bit, and in this particular case, I'm no longer going to close all. I'm going to suppress this right here, okay, and I'm going to turn on hold on. Okay, and I'm going to try and get a number of different profiles all in the same graph right here, because I'm not going to close it. So I'm going to change it to 0.01, 0.01, 0.2, 0.3, now we'll skip a few, 0.5, 0.1, 0.2, okay, and then of course the last one, 0.5. Okay, so it looks then, based upon all these different values of dx that I've used, that I'm clearly having too large of a dx value to make it converge, in the sense that it's not stable and consistent. And hopefully you kind of saw that progression over time. So I'm going to go back to 0.1. Okay, I'm going to close all up again, and we'll take a look at this output right here. Okay, so again, it's getting closer to almost being converged, but the range is still not bounded, so I need to go much smaller than 0.1. And we'll go to 0.01. And finally, we're actually to a value that is going to try to converge. All right, so we can see then that it starts off at 2. Let's first of all check this. Y is a value that starts off at 2. That's good. It should start off at 2. But what is the very first slope? Well, the very first slope is positive. It's going to be the very first one at dy dx. Okay? And that's going to be the value of v. Well, the very first value of v is what? 4. So we expect then this slope right here, the very first, I'm going to zoom in on it right here. Okay, going from 0 to 0.1. Okay. Oops. I want to turn that off. It's going from here all the way up to here. Okay. And we need to take a look at what the slope is. Well, let's take a look at the rise over run. Okay, and the rise is going to be from 2 to 2.04. The run is 0.04, so sure enough, that right there, that little segment from here to here, has a slope of 4. That's because v, okay, our other dimension, okay, drives what that slope is. So what we're going to do now then is try to overlay both of these on the same graph. Okay, so I'm going to turn off, or I'm going to hold on, and I'm going to turn on x versus v. Okay, I'm going to make this one red, and as before, I'm going to keep this one blue. Okay, we'll take a look at these ones. I'm going to change my label because it's going to be either y or v. All right, and so now we've got two values. Okay, we've got a red value right here, and we're going to add a legend here to kind of remind us what that is, but that's the v line, and this right here is the y line. So a second order ordinary differential equation can actually have two profiles. Now, you might only care about the one of them. Okay, in particular, you might only care about y over all time. But you get as kind of an intermediate profile this other value, v over all time, which is the red one. So let me add that legend right here. And the first one is y, and the second one is v. So, and we should maybe choose a location. And I'll set it to be northeast again. Okay, there we go. All right, now we're just going to play a little bit with these intermediate values. Okay, we'll see how things change if I start with a different value of v or a different value of y. The first thing is that I'm going to make the initial to be -4. Okay. Okay, well, sure enough, we know that v starts at -4. Okay, and then it's going to oscillate at an interesting sort of pattern right here. And then the y starts still at 2, because that's how we set it right here, except now its slope is going to be equal to this one right here, -4. Okay. Now, let's talk about the other reason. Why does it start to reverse? Well, let's talk about the very first value right here. Okay. The very first dv, we had it set at -4, okay, but eventually it starts going positive, in the sense that, okay, if this v right here is already -4, this whole term right here becomes, well, positive 2.4. Okay, and if y is already set at 2, well, then this is going to be 16 right here. Okay, so slowly over time, this y value, if I pop up the thing again, okay, the y is, so this value right here y is going to decrease until it crosses the x-axis, and then from then on out, this component is going to be positive, which will add, okay, through a slope, increasing the v-value. Which means then that this point right here when it crosses the x-axis is going to be coincident with this value right here. So effectively these two sinusoids, which are decaying with time, okay, are going to be 90 degrees out of phase. And you see this a lot of times in terms of pendulums, which we'll do later in a future example.